Okay, so this thing is, what I have here in purple is original function f, and the purpose of this discussion is for us to try and understand what this g of x is. So the purple line is f, it's the integrand of this thing. G is the function defined by this integral exactly from the statement of the fundamental theorem of calculus part 1. What I want to do is animate the x value. So what I'm getting in this area here is that's an x value, and I'm sliding it to the right. The value of g should be that area, right? That's what the value of g is. And what we want to do is analyze why the shape of the curve, this is the curve g that's emerging, why the shape of the curve is what it is based on the shape of f. That's kind of the purpose of this whole discussion. So if you take a look, sliding left to right, when I start out at x equals 0, there's nothing to show. And that means that the g value is down here at 0, 0, right? Because the area between 0 and 0 is 0, so there's nothing to show. As I progress to the right from 0, I start to accumulate area, and I'm showing that here in purple. And the blue curve, which is supposed to be the graph of g, is starting to elevate. And since we see that f is not only positive, so I'm accumulating positive area, but increasing, we're expecting the graph of g to be concave up. And that's going to happen until I reach that maximum of f, which is happening roughly there, and the concavity should shift. So what we should be seeing here is we should be seeing this inflection point on the graph of g corresponding to a maximum on the graph of f. In this case, they exactly coincided. That was sort of a coincidence. As I continue, and
that's what it changes concavity, right?
That's exactly where g changes concavity, right? And that happens because f changes from increasing to decreasing. So I'm changing from a state of accumulating area at an increasing rate to a state of accumulating area at an increasing rate over this range to a state of accumulating area at a decreasing rate. I'm still accumulating area until I reach that point, right? What happens as I cross through that point, this particular x value, is my f function crosses below the axis, right? And that means that my integral will register the area that it accumulates as negative. So I'm now expecting my cumulative area function, which is g, to start going downhill. And that's what happens as I cross this thing. So what we can see is the maximum here on the g function is corresponding to this root on the f function.
So basically the slope is decreasing when the area is decreasing, and it's increasing when the area is increasing.
The slope of g is negative when the area under f is below the x-axis, right? And that's because the construction of the definite integral registers that as a negative value. So my cumulative collection of area is starting to decrease. And that corresponds to the slope of g being negative. That's right. So it's going to continue this direction. And as we continue, now, again, because f is now negative, so we're accumulating negative area, and it's pulling away from the x-axis. So we're accumulating negative area, or we're losing area at an increasing rate. The concavity of my g function should be negative, right? Until I reach roughly this minimum point, right? And that minimum should correspond to another point of inflection on g. And we'd see that if we pass through, right? So over this range, kind of between x equals 5 and that next root, my f function is still below the axis, right? So I'm still continuing to lose area because the area accumulated is registering as negative, but I'm losing it at a decreasing rate. So my concavity of g has shifted to concave up, right? And if you keep continuing this way, you can sketch out this graph, right? This root of f is corresponding to this minimum of g, and you can keep moving in that direction. And there's another interesting thing that happens here. Let me see if I could think about this. So at this stage in the game, I only had positive area. It's like the poker hands, I was only winning. I was only winning. Then I started to lose. It's an interesting question to think about a little bit. What are the conditions on F, on the purple curve, that will make my G graph fall below the x-axis? So what happens right where that G curve hits the x-axis?
Areas cancel out.
The areas cancel out, exactly. This area, which was negative area, is the same absolute value as that area, which was the positive. So you could take a look at peaks that are above the axis, x-axis, and peaks that are below the x-axis. This second peak, or valley, whatever, has an area which is bigger than this area. So I'm expecting the y values on the G curve to definitely cross below the axis, right? And they do. And so then you can sort of continue with that line of thinking. So I've lost more than I gained here. Then I started winning again, but I'm definitely...
Are you still losing in a way? Because you haven't made up for the loss.
Good. I'm still in the hole. I'm still definitely in the red because the amount that I lost over this stretch exceeds the amount that I gained over this stretch. So the y value on G is still negative. That's fine. Now I'm starting to win, so I'm starting to dig my way out of that hole. Right?
So the point where the areas cancel out, that's where you basically return to 0 and you keep losing again.
That's right. The point where the areas canceled out, and that happened once back here, right? That was the point where my wins in my first session canceled out with my losses in sort of my second session, my losing streak. And then later, I kept losing for a while, so I'm in the hole, and then I started winning. There's another cancel out point, right? The amount that I won here, the amount that I won here and here canceled out with the amount that I lost in this region. And then I continue to win. Those are the roots of G. Yeah, those are the places where the areas cancel out. And that doesn't really show up nicely in a derivative situation, but it's something that's worthwhile to kind of think about, that you can approximate the y values on the G function by looking at relative area sizes. Maybe hard to guess the area, but relatively you can see which peak is bigger than which valley, things like that. And so as we continue to the right here, we're approaching another maximum point of F. Right? So on this region, I was winning because my F values were positive, and I was winning at an increasing rate. Every subsequent hand in my poker game, I won more and more and more and more. So that meant that the concavity of G should be up, concave up, until I reached this maximum, right? And that corresponded to an inflection point again. So, and after that, I've started losing a bunch. That's happening here. I've started winning not as fast. Started winning at a decreasing rate, and that's why my concavity on G shifted. And you continue in this way. And the goal of this is to, I think, at one level, sort of have some intuitive working knowledge of what that means, which I think is pretty hard at first because there's lots of symbols and most of them are new. And on the next level, you start to realize that the features on the graphs of F and G, right, for example, a maximum on the graph of G corresponded to a root on the graph of F. To the left of that maximum, the slope of G was positive. Well, that's because the values of F were positive. Right? To the right of that maximum, the slope on the graph of G was negative, and that's because the values on F were negative. So the relationship here is that F should be the derivative of G, right? Which is precisely what the fundamental theorem of calculus says. It says that F can be found by the derivative of G. It's precisely what this says. This is the fundamental theorem of calculus.
F is the antiderivative, right?
No, G is the antiderivative of F. Yeah, G is the antiderivative of F. Questions, thoughts? And so likewise, I guess you can see inflection points, right? Inflection points on G, for example, this one, are corresponding to places where F changes from increasing to decreasing.
So the roots of G are also where the displacement is 0?
The roots of G are, yes, so in the context where, for example, F represented the velocity function, then G was representing the position function. or the displacement function position in this case if I started at time 0. And the places where g had roots corresponded to places where the displacement was 0. In other words, I crossed my starting point. My particle crossed the starting point at that point. Yeah, so that's an interpretation in the context of particle moving along a line. Yeah? Questions, comments?